press the bell icon on the YouTube app and never miss another update.
In the previous class, we have discussed about certain basic concepts, right? Now we have let us discuss about the equation of a progressive wave. So far we have discussed that a wave that continuously propagates through a medium in the same direction without any change in its amplitude or constant amplitude is called progressive waves. And we have also discussed the various characteristics of a progressive wave. Here generally we are considering mechanical wave. Here progressive wave means it may be a longitudinal progressive wave or it may be a transverse progressive wave, right? The difference between them is that a transverse progressive wave exhibits polarization, whereas longitudinal progressive wave does not exhibit polarization, right? So now we will take that equation for progressive wave. And of course, for board examination, it is a 5 marks question, right? The question will be like that: obtain an expression for, or obtain equation of a progressive wave, right? Now, let us consider a plane wave. Right, it is a two-dimensional wave, a plane wave, of amplitude A, traveling with a uniform velocity V along positive x direction that I will show in the figure. So this wave can be represented like this by plotting a graph of displacement of various particles y, against the time. This is a positive x axis, right? So let O be the origin or the first particle to be started vibrating. Now let the wave propagates continuously through a medium with a velocity v in positive x direction, right? Now at time t is equal to 0, so O is at rest. It is not at all vibrating, right? When the particle O or at the origin is disturbed at time t is equal to 0, it began to vibrate, right? Now we have displacement of particle, displacement of particle O, at time t is given by, y is equal to a sin omega t. Let us take it as equation 1. So we have derived this equation of simple harmonic motion, right, in the previous chapter, oscillation. So where omega is equal to 2 pi by t, or it is equal to 2 pi f, where t is a period of wave and f is a frequency of wave. However, equation 1 gives displacement of the particle O, that is the particle only at origin. It cannot give, right, displacement of any other particle, because when a progressive wave is propagating through a medium, after some time all the particles of the medium began to vibrate about their mean position. Since different particles are disturbed or set into vibration at different instants of time, right, they will have different states of vibration or different phase, right. So we need a general equation which can give displacement of any particle of propagating medium at any instant of time t. Now let us consider a particle at p, which is at a distance x from the particle O. Right. Now the wave is propagating with a velocity v, that means disturbance is propagating with a velocity v. So when the particle O begins to vibrate, now it collides with the second particle, and little later second particle vibrate, third particle, fourth particle, fifth particle, and so on. So the disturbance goes from first to second particle, second to third particle, third to fourth particle with a velocity v, right. Now the time taken by the disturbance or wave to reach the point P is x by v. We know that distance travelled is equal to, velocity is equal to distance travelled by time taken, or time taken is equal to displacement by velocity, or here the distance travelled by the disturbance is x, velocity v, this is x by v. So that is the time, right, taken by disturbance to reach P is x by v second. Time t is s by v second. Now, so as the particle P began to vibrate after x by v second, so that the state of vibration of particle P at any instant of time t, right, is same as the state of vibration of the particle, right, at O at a slightly earlier time x by v second. For an example, we will take this x by v is equal to 2 seconds, right. Now, so the disturbance takes 2 seconds to reach the point P after O has disturbed. Suppose at any instant of time t is equal to 6 seconds, we say, right, the state of vibration of the point particle P after 6 seconds from 0, right, is the same as the state of vibration of the particle, right, at the earlier time 6 minus 2, that is the 4 second, right. It is because, so when we consider the 6 second, that particle P, right, the disturbance to reach the particle P is 2 seconds. So after 6 seconds, right, the disturbance of state of vibration of the particle P right, at 6 second is same as the state of vibration of the particle O at 4 second, right. Therefore, right now, therefore, we can write state of vibration of P at time T is same as the state of vibration of O at time T minus x by V second. That means that time at which the phase of O equal to phase of T at T is T by 6 pi. So, replacing this T by T minus x by V in this equation, we can get the displacement of the particle P at an instant of time T. Therefore, we can write displacement of P at time T, that is y is equal to A sin omega, right, into, right, T minus x by V. Let us take it as equation number 2. This equation number 2, right, is called equation of progressive wave, right. That equation of progressive wave, that y is equal to A sin omega into T minus x by V. Here A is amplitude, omega is angular velocity, x is the distance of the particle from the origin, V is the wave velocity, and y is the displacement at time t. You see, we are having two equations on the board. The equation 1 is applicable to, right, oscillation of a particle when single particle is oscillating, right. Now its position is taken to be, its mean position is taken to be at the origin, so that x is equal to 0. Similarly, this equation number 2, right, is applicable for the displacement of any particle of a propagating medium through which a progressive wave is propagating, right. So here y is the displacement of a particle at a distance x from the origin at any instant of time t. Suppose if the particle P, say, lies at the origin for an instance, then what is the value of x? The value of x is equal to 0. When we put the value of x is equal to 0, this term becomes 0. T minus 0 is equal to t. The equation 2 becomes equation 1 when x is equal to 0, right. You got my point clear, right? When we put x is equal to 0, that is the particle at the origin O, then equation 1, 2 becomes equation 1. Remember that whenever we are finding the displacement of a particle executing simple harmonic motion, we use this equation y is equal to A sin omega t, or of course y is equal to A cos omega t. But whenever we are finding displacement of a particle of a propagating medium in which a progressive wave is propagating, we are using equation 2, y is equal to A sin omega into t minus x by v. Is that clear? No. Now, note, we'll take. So, point number 1, right? Now, we have equation of progressive wave. Y is equal to A sin omega into t minus x by b, right? So, here this equation gives, right, remember this equation gives displacement y of a particle of medium at distance x from the origin at time t, at time t. So, this is a function of, right, y, x and t. This equation gives displacement y of a particle at a distance x from the origin at any instant of time t, right. Suppose if the wave is propagating along a negative x direction, if the wave is propagating along negative x direction, then, right, in this equation the value of y becomes negative, minus into minus becomes plus. Now, the equation becomes y is equal to a sin omega into t plus x by b. What is the difference between these two equations? All the terms are same. Here we are having negative sign t minus x by b. Here we are having positive sign t plus x by b. Here the negative sign is indicating that the wave is propagating along positive x direction. Here, negative. Here the positive sign is indicating that the wave is propagating along negative x direction, right. So, remember that whenever we are dealing with the overlapping or superposition of two or more waves, the waves may be traveling in the same direction or the waves may be traveling in opposite direction. If the waves are traveling in opposite direction, means one is along positive x-axis represented by this equation and the other one is along negative axis represented by this equation. If both the waves are traveling along positive x direction, then they are represented by the equation 1, right. Is that clear? Now, we will take different forms of equation of progressive wave, generally called as a wave equation. Equation of simple harmonic motion, y is equal to a sin omega t, and equation of a progressive wave or wave equation is y is equal to a sin omega into t minus x by v, right. Now, the first form we have this equation y is equal to a sine omega into t minus x by v. This is the original form of equation where we know that a is amplitude, right? Omega is equal to 2 pi by t is equal to 2 pi f angular velocity, right? V is right wave velocity or velocity of the wave, right? X is the displacement, distance of the particle from the origin, and t is the time interval. Now second one, this equation can be written as y is equal to a sine. Omega can be replaced by 2 pi f into t minus x by v. This is equation 2. The second form, the same wave equation can be written in terms of frequency. F is equal to a sine 2 pi f, right, where f is a frequency. Now the third one is, right, we can write y is equal to a sine. Instead of taking 2 pi f, if we take 2 pi by t, this is 2 pi by t into t minus x by v, or y is equal to a sine, right, 2 pi into, by taking the t inside, t by t minus x by v into t, right. But we know that v is equal to lambda by t. By definition, right, wave velocity is the distance traveled by time taken, and also by definition wavelength is the distance traveled by the wave in a time interval equal to its time period, or we have v into t is equal to lambda, where lambda is wavelength of light. Therefore, we have y is equal to a sine 2 pi into t by t minus x by lambda, right. This is equation 3, right. Now where lambda is a wavelength of light, lambda is wavelength of wave. So this is the third form of the equation. It gives the displacement or wave equation in terms of time period t and wavelength lambda. So here again we take t is that is the time period. That is the third equation, right. Now the fourth equation. Now the equation 1 can be written as y is equal to a sine, taking omega inside, omega t minus omega into x by v, omega t into, right, omega t minus omega x by v, or right, y is equal to a sine omega t minus kx, right. This is the fourth form of the equation. So here, so k is equal to, from this equation, omega by v. For a given wave, propagating through a medium, omega is constant, right? It depends upon the vibrating body producing the wave, that is omega is equal to 2 pi f. And we know that a progressive wave travels with a constant velocity in a given medium. Therefore, the ratio of omega to v, right, is another constant, that is k, right. Now this is equal to omega, it is 2 pi f. Now we have this from the wave velocity, right? This is omega is equal to 2 pi f and v is equal to lambda f. Substituting here, v is equal to lambda into f, f get cancelled, or k is equal to 2 pi by lambda, right? So this k is equal to 2 pi by lambda, or omega v is called propagation constant. It is constant for a given wave in a given medium and it is called as propagation constant, right? Now it represents the 2 pi is the change in phase of a particle, right? And lambda is the wavelength. When lambda, this distance is taken to be 1 meter, then propagation constant, is defined as the change in phase per unit length of medium. It is the change in phase per unit length of medium. So SI unit of K is radian per meter, because 2 pi represents the angle or phase and lambda is measured in meter. It is radian per meter. It is a very important concept in the wave equation. So though depending upon the situation, we can use the 4 different forms of the same wave equation, right? The same equation, right, expressed in terms of different physical quantities, right? But the most general equation we use for the study of progressive wave is y is equal to, right, a sin omega t minus kx, right? It is the more general equation, right? Right. So now we have general form of wave equation, that y is equal to a sin omega t minus kx. Here the negative sign indicates that, right, the wave is propagating along positive x direction. Sometimes this equation can be written as y is equal to a sin omega t plus kx, right? That means to say the wave is now propagating along negative x direction, right? If we take equation 1 and equation 2, equation 1 represents wave is propagating along positive x direction and equation 2 represents wave is propagating along the negative x direction, right? So these two waves are traveling exactly in opposite direction. But for general consideration, single wave, we take the wave is propagating along positive x direction. Now we see that equation here. We know that A is amplitude. Now that omega is equal to 2 pi f, it gives frequency of wave, right? This gives frequency of waves. Now k is equal to 2 pi by lambda, so gives, right, wavelength of wave. And again we have v is equal to lambda into f, right? That gives wave velocity. That means this equation includes, right, all the characteristic parameters of a wave like amplitude, frequency, period, wavelength, angular velocity, right, wave velocity, etc. All the information can be obtained. Suppose, for example, if I say y is equal to 0.5, right, sine, right, 100, right, t minus, right, 4 pi x. Now here in this equation, A is equal to 0.5, right, meter, that is the amplitude I have taken in SI system. Now when we compare this equation with the standard equation, now this omega is equal to 100 radian per second, right? That means F is equal to, right, omega by 2 pi. With that we can calculate the frequency. Now k is equal to, right, compare this one, k is equal to 4 pi, right, radian per meter, and we have, right, lambda is equal to 2 pi by k. Substituting 4 pi here, 2 pi by 4 pi, 2 by 4, 1 by 2, that is lambda is equal to 0.5 meter, right. Then we have, once we find frequency and wavelength, we have V is equal to lambda into F, right. So by comparing the given equation of a wave with the standard equation, we can get all the wave parameters of the wave, starting from amplitude, angular velocity, frequency, propagation constant, wavelength, right, wave velocity, and even we can calculate the time period. Once we know the value of frequency, then the time period t is equal to 1 by f, and this is the use of this equation while solving the numerical problem, right? While solving the numerical problem regarding a progressive wave, when equation is given and we need to find wave parameters like amplitude, wavelength, frequency, wave velocity, etc., then we can compare the given equation with the standard equation, and by solving it we can obtain all wave parameters. Is that clear? Right. Now, so far we have discussed about phase of a vibrating particle. Now we will take another term, that is phase difference. So delta phi, it is represented. Right. Now let us consider a progressive wave propagating through a medium, right? This is origin O, Y, T, right? Now here the different particles are vibrating at different phases. We know from the characteristic property of a progressive wave, when a progressive wave propagates through a medium, different particles are disturbed at different instant of time, and at any given instant of time they have different states of vibration or phase. Now let us consider there is a particle at P1 having a phase difference phi 1, which is at a distance x1 from the origin, and another particle P2 having the phase phi 2 at any instant of time, which is at a distance x2 from the origin, right here. Now, when two particles of propagating medium are in different states of vibration, then there exists a phase difference between the two particles, right? Now, so phase difference between any two vibrating particles of propagating medium is the any two propagating medium is the difference in their states of vibration or phase. So here phase difference between particle P1 and P2 is delta phi is equal to phi 2 minus phi 1, where phi 2 is the phase of the particle P2 at time t and phi 1 is the phase of the particle at time t1, right? So phase difference between any two vibrating particles of a propagating medium due to a progressive wave propagating through it is a difference in the state of vibration of the particle, right? It is because when two particles, right, of propagating medium are in different states of vibration or phase, obviously there exists a phase difference between the two particles. Just like when a fluid is flowing, right, if there are 2 points at different pressures, one is at higher pressure and one is at lower pressure, then there exists a pressure difference. That pressure difference causes the flow of fluid. I am giving an example, just how we are taking. Just like, right, when 2 points in an electric field are 2 different electric potential, there exists a a difference in potentials called potential difference. That potential difference we can call it as a voltage, right? In a similar way, right, if two particles of propagating medium are in different states of vibration or phases, then there exists a phase difference between them, right? The phase difference between the two particles is a phase of one particle minus a phase of the other particle, right? Here the phase difference between these two particles is right phi 2 minus phi 1. Again we are having the term path difference, right, denoted by delta x. So if two particles are vibrating with different phase, then they cannot have the same position. Obviously they have different positions, right, and of course they are separated by a certain distance. We see here the particle P2 is at a distance x2, the particle P1 at a distance x2, and the two particles P2 and P1 are separated by a distance of x2 minus x1. So the distance between two vibrating particles in a medium, right, is called the path difference between two particles, right. So here path difference between the particles P1 and P2 is delta x is equal to x2 minus x1, right. The path difference is right x2 minus x1. So generally this distance is lambda, and the phase at that point is 2 pi, right. So when we consider a particle at O and a particle at A, we see the phase of the particle is 0. The phase of the particle A is 2 pi because it has completed one vibration. So phase difference between O and A is 2 pi minus 0, that is equal to 2 pi. Now what is the path difference between this O and A? Obviously it is equal to wavelength, right. So the path difference between the particles O and A is lambda. Therefore, right, this phase difference is expressed in terms of fraction of angle 2 pi, and path difference is expressed in terms of fraction of wavelength. So keeping that same figure, I will take note 1, right. So phase difference is expressed, right, in terms of fraction of 2 pi. That means from figure, phase difference between, right, O and A, that is delta phi is equal to 2 pi minus 0 is equal to 2 pi. Number 2, path difference is expressed in terms of fraction of lambda, right, that is wavelength. For example, path difference between O and A, that is delta x is equal to, right, that is equal to lambda. So x2 is equal to lambda, x1 is equal to 0, x2 minus x1 is equal to 0. Here phi 2 is equal to 2 pi, phi 1 is equal to 0, phi 2 minus 0 is equal to, right, 2 pi. Is that clear? Remember that phase difference is expressed in terms of fraction of 2 pi and its unit is radian, right, or sometimes it may be expressed in degree, right. That means if the phase difference is 0, it is 2 pi radian, that is 2 into 3.14 radian, or in terms of degree it becomes 2 into 180, that is equal to 360 degrees. And path difference is expressed in terms of wavelength and it is measured in meter. Now, let us find the relation between phase difference and path difference of two vibrating particles in a propagating medium due to a progressive wave, right. Now, relation between phase difference delta phi and path difference delta x. Again, let us consider a wave, progressive wave propagating through a medium. Let O be the origin. A graph of displacement against time, right, can be represented like this. Right. Now let us consider a particle P1 at distance x1 having the phase phi at any instant of time t1, that is phi 1. Now let us consider a particle P2 at a distance x2 having the phase phi, right. Now here phase difference between the two particles delta phi is equal to phi 2 minus phi 1 and the path difference between the two particles delta x is equal to x2 minus x1. Right. Now, we have wave equation. We have wave equation. So, y is equal to a sine omega t minus kx, where a is amplitude, right, omega is, right, angular frequency, right, k is propagation constant and x is the position of the particle, right. Here, right, this omega t minus kx, right, it represents phase. It represents phase at time t1. Therefore, so phase of P1 at T, right, phi 1 is equal to omega T minus K x1, because for P1 and P2 they vibrate with the same amplitude, they vibrate with the same period, right, the lambda is constant, that is K is propagation constant, right. Now, phase of T2 at time t. So phi 2 is equal to omega t minus k x2, right. As the position changes, right, the phase changes. Now phase difference between the particles P1 and P2, delta phi is equal to, right, it is phi 2 minus phi 1, or delta phi is equal to, right, phi 2 omega t minus kx2 minus omega t minus kx1, or delta phi is equal to omega t minus kx2 minus omega t plus kx1. Omega t get cancels, delta phi is equal to, right. Now this is right, k into x1 minus x2. So both x1 minus x2 or x2 minus x1 represents the path difference. Therefore, this can be written as k is equal to x2 minus x1, right? Because here path difference is not the displacement. It is the distance between the two particles. It cannot be negative. From figure, if we take x1 minus x2, right, it becomes negative, right. Therefore, we are taking x2 minus x1, or delta phi is equal to, what is the value of k? 2 pi by lambda. What is x2 minus x1? That is delta. I will write it here. Now that delta phi is equal to, but we have k, propagation constant, 2 pi by lambda, and this delta x2 minus x1, that is equal to delta x. So this is the relation between phase difference and path difference. That is, right here I can write so. Is that clear, that derivation? Now, so writing this equation in word, we have phase difference is equal to 2 pi by lambda into path difference. So phase difference is equal to 2 pi by lambda into path difference. Now we will take it as note. Now we have delta phi is equal to lambda by 2 pi by lambda into delta x, or delta x is equal to lambda by 2 pi into delta phi. Here what is delta x? Path difference. Delta phi phase difference. Therefore, path difference is also equal to lambda by 2 pi into phase difference, right? And remember that this phase difference delta phi is expressed in terms of 2 pi. Path difference is expressed in terms of lambda. The relation between path difference and phase difference, right, involves both lambda and 2 pi, right. This is the very important relation, right. From these equations, if we know the distance between the two particles of propagating medium, that is the path difference, we can find the phase difference, or if we know phase difference, then we can find the path difference. So this is a very important relation, right. We should know that one, right. Is that clear? In the next class, right, again we will discuss how to find phase difference and path difference, right, practically, by using a progressive way, right. So thank you very much. Remember that in this class we have discussed equation of a progressive wave, and remember the difference between equation of simple harmonic motion, equation of progressive wave, and different forms of progressive wave, phase difference between two vibrating particles, path difference between two vibrating particles, and the relation between phase difference and path difference. Okay, thank you. We shall continue in the next class.